energetics of the flow is physical. Reynolds invented it. So what could be wrong with it? Legion of problems. One is you're studying infinite dimensional state spaces. And this projects it on 2. Or 3 if you count energy as 1, and then these dissipation rates as 2 other axes. And say, okay, what the hell? You want infinite many dimensions? You obtain this by integrating by parts. I'll just keep doing it. I'll give you a zillion equations. It turns out it's possible to get started, but hard because it just takes more time derivatives and insert equations on motions. But it's hard to actually study the second time derivative, third time derivative of this. They get kind of funkier and less physical as you go along. There are some kind of high moments you have to compute. It's not at all obvious that they're experimentally accessible. You can imagine that you measure speed at which energy changes in time, but second, third, fourth derivative of this on experimental data won't be very useful. So how to generalize? So it has a bad property of cheap ideas. It's really easy to explain, but then you can't go any place visit. You can just get a few other ideas. Next. If I take 2 things which are very far apart, this is a crazy scheme because it tries to put everybody on diagonal or close to the diagonal. Because all the averages like to be close to this diagonal, it just enforces it by equilibration of energy in, energy out. So you can take a state where I have 3 vortices in that corner and another state where one is there and somebody is there, and they can have same energy dissipation rate, who knows. So they can be very close in these kind of plots, power dissipation plot. If they're very far apart, then they won't be close in the state space because they're very far if they're far apart in one projection, they cannot be close. So that's good. But then zillion things will look very close, but they could be totally different physically. The next thing is, it makes you feel too confident about your theory, because everything is being scrunched onto this one line, and it's being kind of bounded very easily by laminar solution and the craziest solution you have. Almost any calculation will give you a reasonable expectation value for these quantities. So the first paper that found periodic orbit in a fluid flow computed one of these green averages, and it turned out to be good to few percent compared to long time expectation value of power dissipation plot. That's very misleading. And the other thing that you compute could be very different. It just so happens that these particular observables are just kind of scrunching everything in a very small state space. It might seem very natural in fluid dynamics that I take velocity square and I integrate it over the space. But think a little bit about it if you were doing this in classical mechanics. Suppose you're interested in celestial mechanics. So there are sun, there are planets, there are comets, there may be 20 bodies. And now a plumber comes in and says, oh, that's very simple. What you do is you take kinetic energy of every planet. So you take mass of the planet, and you take its kinetic energy over 2. You look at this. This fluctuates in time, and that's it. That's the content of celestial mechanics. Right? In fluid dynamics, we accept it, that, thing fluctuates, and I just care about that object. You would be insane to do celestial mechanics because it's a clockwork. And you have very specific things to predict. You have to predict who is going to be where at what time. And you have to predict where this thing will be here 3 billion years from now or not. Will this exist on scales which are much longer than I can integrate equations or not? And it's equally useless here. So what you do there is you look at what we call phase space in classical mechanics. I realize the number of degrees that I have to study is 3 degrees for position of every body and 3 degrees for its momentum. And there's some conservation laws which decreases the number, and I have to quotient the symmetries, I have to go to center of mass, I have to quotient the rotations around center of mass. And then I start working. It's hard, but I will predict where Venus and Mars are at the moment that's of importance to us for a variety of reasons. And I'll predict, and that's one of the great triumphs of modern chaos theory, I'll be able to discuss what happens for very long times. So, for example, celestial system, these planets will not be there forever. We will lose planets. The chaos will... We have a probabilistic estimate of kind that theory that I developed gives to you, but very hard, very beautiful work. Don't be seduced by cheap ideas. If somebody can explain to you something in 30 minutes and it just makes total sense, be very suspicious, because the problem of turbulence obviously is much richer than that. So in turbulence, we need to understand in detail how this clockwork works, because we would like to decrease the dissipation rate, for example, which means we would like to bring the turbulent flow in some other state, maybe laminar or maybe some other state, which is less dissipative. So if my oil pipe has 5% less dissipation, $100 million ahead. So I need to know how it works. If I'm trying to do this in cardiac dynamics, I have some PDEs for activity on the heart, and I want to move it from one type of activity to the other, and to do that, I need to know in detail what it's doing. Being told that my average heart rate is 80 or 0 is not very useful information. If it's 0, I'm probably not doing very well, but if it's fluctuating, statistical ideas don't make much sense in this. You really need to get a handle and work on it. And this is what this kind of theory, when it works, it's very hard to apply, but when it works, these are the kind of solutions you should be working on.